Am I audible to all of you guys? Okay, cool. So let me share my screen, guys. Yeah, thank you, guys. Okay, so I hope my screen is visible to all of you guys, right? Great. So let's begin with the session, guys. So yesterday, we have discussed the things related to the RNN, recurrent neural network, and we also saw how the different deep learning based architectures will replicate the human brain behavior, right? So we saw something called as a ANN, artificial neural network, which will replicate temporal lobe. We also saw something called as a CNN, which is a convolutional neural network that will replicate occipital lobe. And then we have discussed RNN in a detailed manner, which is a recurrent neural network that is the replica of frontal lobe, right? And apart from that, we saw a couple of details related to the recurrent neural network. So how it looks like, why we are calling it as a recurrent, and then we saw what are the issues associated with this RNN network. So if I just recall you, let me add a new slide. Okay. So if I just quickly recall you how the RNN network looks like. So it is represented with, like, let's say this is your input layer. The output of input layer goes to the hidden layer, and the output of hidden layer goes to the output layer. And then since it is a recurrent, so whatever output hidden layer generates, that to the next hidden layer node, right? So it's a graphical representation of RNN network. And then if you expand this network looks like, uh, if you have a multiple layers. So let's say we have a layer one where we have the input node, then first hidden layer node, and then first output layer node. So let's say hidden layer one, and let's say here we have a second layer, hidden layer two, input two, and let's say here we have a output two, hidden layer three, hidden layer four, okay. So these are, guys, input one, input two, input three, input four. These are the hidden layer 1, 2, 3, 4, and these are the output layer node 1, output layer node 2, output load output layer node 3, and output node 4. And the connections will be like, if you provide input to the node of the first hidden layer, they will do the calculation, and whatever output is being generated, that output will be fed to the uh, output layer node O1 as well as the input to the second layer hidden nodes. That is the meaning of recurrent, right? So in that way, the second layer, like a hidden layer node, will memorize the output or the information present at the first layer hidden nodes. And the same calculation the hidden layer node for the second layer will do. So for next of the hidden layer nodes, there will be two inputs. One of the input is coming from input layer. Another input is coming from the previous hidden layer output. Right? So there will be two input for each and every hidden layer node, except the first layer node. Since because before this first layer, we don't have any input, right? So for rest of the layers, so the whatever output this H2 will generate, that output will goes to the output layer node of layer 2, as well as it will be input to the next layer hidden layer nodes, right? Same for S3. Whatever output S3 will generate, that will be the input to the output node of the layer 3, as well as the next layer hidden nodes, right? So this is the meaning of recurrent. So you can see here, for rest of the hidden layer nodes, there will be two input. One of the input is coming from the input layer. Another input is coming from the previous hidden layer node, right? So this is the typical recurrent neural network architecture. And then we saw what is the problem with this recurrent neural network architecture. The problem is basically vanishing gradient and exploding gradient. So whatever weights we have for these recurrent layer, so we are calling as a W recurrent, REC, WREC. And one of the property of the RNA network is the weights will get shared. So whatever weight we have for this hidden layer node, so all of the weights will be same. So the issue is like either vanishing gradient problem, vanishing gradient problem, or exploding gradient problem. So if your recurring weight is less than 1, right? So like 0. Let's say 2 or 0.9, or let's say 0.008, something like that. So once the weight is being updated, and guys, how the weight is being updated? What is the mechanism? In neural network, the weight is being updated. What we call that mechanism? Do you guys recall the name? Anyone? Yes, Himanshu, it's a back propagation. Yes, exactly, guys. Guys, this term is very important, back propagation. Right? This term is very important, back propagation. So once, with the help of the back propagation, when the weight is being adjusted, there will be, like at the backend, there will be gradient calculation. And this gradient calculation will depend upon the chain rule of the derivation. So if your weights value, this recurring weight value is less than 1 or very small, so in that case, if you multiply these gradient values which are less than 1, so ultimately you will be landing to a value which is very close to the 0. So that means your weight updation will be almost negligible. That is something we are calling as a vanishing gradient. That means the weight updation will close to 0, right? And the reverse case of this is something we are calling as a exploding gradient, where the recurrent weight, if it is greater than 1, so let's say 1.9, 1.8, or let's say 2.2. So if you have a number of recurring weights which are greater than 1, and if you multiply all of these values, so ultimately the weight value, or the optimum weight value, will be very, very large, right? So if the value is very, very large, so probably you are not landing with the optimum value. Again, it will take ample amount of time to converge. So that particular issue we call it as a exploding gradient. And then we also saw what are the issues with these these problems, and what will be the possible solutions, right? So one of the possible solution is which is the best possible solution. Like most of the time we are going with that particular option. That is nothing but let's choose gated architecture, gated neural network architecture, right? Gated neural network architecture. Now, when it comes to the gated neural network architecture, so here we have two kinds of the architecture. First one is called as a LSTM architecture or LSTM neural network, and second one is a GRU. LSTM stands for long short term memory. Long short term memory. GRU stands for gated recurrent unit. Gated recurrent unit. Okay. So now we are going to study about LSTM, as well as I will show you like how this GRU neural network architecture looks like. But out of these two guys, most of the times, or you can say more than 90% of times, we go with the LSTM kind of a architecture, right? So most of the examples you can find with the LSTM when it comes to choose between LSTM or GRU. Okay, this is one thing. Now, before starting with this part, let me recall you one more very important point. But before that, let me just see. Okay, yeah. Okay, let me remind you one very important point, guys. If you recall, when I discussed the things related to the RNN, so there I told you we use RNN in case of a time series forecasting, as well as we can use RNN for the text analytics or text analysis, right? And then I also explained you one a very important term, that is we are calling these two applications as the sequential data analysis, right? So RNN is used for sequential data analysis, right? Now let's understand what is the meaning of sequential data analysis, because whatever architecture you are going to study it further, like we have saw what is the RNN, and today we are going to see what is the LSTM and GRU, and then I will show you a couple of practical examples with LSTM, right? So I will take two examples, one with the numerical data, another with the text data. So these are the typical applications of the sequential data analysis or sequential data modeling, right? Sequential data modeling. So first, let's understand what is the meaning of sequential data, and then let's come back to LSTM part, right? So up to this point, guys, any doubt or any queries, anyone? Or we are good to go? Let me also check with YouTube, guys. Yeah, good evening, guys. Okay, so okay, so I guess things are pretty much clear to you guys since I haven't received any questions. Great. So guys, let's first understand what is the meaning of sequential data. Now, to understand the sequential data, there is one more term which is called as a cross-sectional data. So we have two terms. One is called as a cross-sectional data. Another one is a sequential data. Right? Now let's first understand what is a cross-sectional data. So let's suppose, guys, we have a data, right? We have a data set like let's say it's a university data where we have a records for different students. So let's suppose we have a different students and there some details. So these are the different records we have. Let's say this is a student one. So this particular column is for the student. Student one, student two, student three, student four, student five, student six, and so on. Right? And let's say here we have a age of the student. Let's say 18 years. Let's say 18.5 years. Let's say 19 years. Let's say 17.5 years. Right? So in that way, we have a age of the students. Let's say here we have a let's suppose in which course the student is enrolled. Let's say the first student is enrolled in the course. There is something called course A. Second student also enrolled in course A. Let's say third student enrolled in course D, course B, and so on. These are some typical kind of a course. And let's say we have a couple of other information like the address and some other details, right? Or let's say we have a like 10th percentage, right? Or 12th percentage. So let's say here we have a 78%, or let's say 81%, let's say 88%, or let's say 72%, something like that. Now see guys, we have this kind of a data where we have a details regarding the different students for a particular university or college. Now, if I ask you one question, can we shuffle the records here? So when I say records, I mean the first row is one record. This is one record for student one. This is second record for student two. Third record for student three. Right? Now, if I ask you, can we shuffle the records? Does that impact? Does that create any impact over this table? So that means if I make the student two as a first record, student one as a second record, or student six at this place, student three at this place, does that make any impact over this table or analysis? No, right? Exactly. Yes, all of you guys are correct. So we can shuffle the records. That doesn't make any impact over the analysis. So that means the data set where the order of the records are not maintained, where the order is not important, that means you can shuffle the records. These kind of a data set we call as a cross-sectional data set. Here, order is not important. Order is not important. That means you can shuffle the records. That won't make any change over the analysis. Right? Sumano, we have a class today, right? So this kind of a data set we call as a cross-sectional data set. Okay. Now see the example of sequential data. Let's suppose, guys, we have a data set where we have a let's say two columns or two features. So here we have a month, and let's say here we have a sales. That means we have a monthly sales for a particular product. And let's suppose the records are like, let's say we have a records like this. Let's say we have a Jan 23, that means January 2023. We have a Feb 2023. We have a March 2023. We have a April 2023. We have a May 2023. We have a June 2023, and so on. Right? And let's say there are some sales. So let's suppose here the sale was a particular sale of a particular product is, let's say 120, and all of these are in thousands, right? And let's say here we have a 150, here we have a let's say 90, let's say here we have a 110, 180, 160, and so on. Some amount of sales. Now, if I ask you guys, can I shuffle the records in this case? That means, can I get the sales for Feb month before Jan, or can I get the sales for Jan month after April? No, right? Because this data is with respect to some time variable. This sales is we are getting for with respect to some time variable, and here the time is month, right? So that means here the data is indexed by the time, and you can't shuffle the time, right? So there will always be Jan month before the Feb. You can't get the sales for Feb month before Jan, right? You can't get the sales for Jan month before April. Oh, sorry, after April. So that means here the data is indexed by the time. Whatever data you have, all of this data is indexed by the time. Now this time, it can be monthly basis, it can be hourly, it can be on second basis, it can be minute basis, it can be yearly basis, quarterly basis, it can be any of the fraction, right? The frequency can be anything. So if your data is indexed by the time, these kind of a data cannot be shuffled. Here, the order is important. This kind of a data be called as a sequential data, right? So here, the data is indexed by the time. Indexed by time. And order is important. Right? So this kind of a data we call as a sequential data. Okay. So this is the example of what you can say with the numerical data. Right? So this is an example of sequential data in terms of the numerical data. If I talk about the text data, so let me also show you the example of text data when it comes to the sequential data. So I'm talking about the sequential data. So guys, let's suppose this is our RNN architecture, for example, or LSTM architecture, or any kind of a neural network architecture, which will analyze the sequence of words. So we have a input data, which is in case of in this case, this is the text data. So let's suppose we have a sentence like, let's meet on lunch, right? So let's say we want to analyze this particular sentence. So why we are calling like this kind of a data as a sequential data analysis? The reason being, in this data, the first word will always be let's. You can't shuffle the order of these words, right? So when we provide the input to this RNN network, the first word will always be the let's. Let's say this word we are having at a time instance t. Then at a time instance t plus 1, that means in the next time instance, we have a next word, which will be the meet. At next time instance, that is t plus 2, we have on. And the next time instance, we have at t plus 3, we have a lunch. You can't shuffle the order, right? So it's a sequence. So the first word will be let's, then meet, then on, then lunch. Right? So in that way, we provide the input to this RNN network if you are processing the text data. That's why we are calling it as a sequential data. And this RNN or LSTM or GRU, these kind of a network will process the sequential data. It may be numerical, it may be text data. Is that clear, guys? What is the meaning of sequential data? Yes, Himanshu. Any queries, guys, to understand what is a sequential data? Okay, cool. So if you guys understood what is a sequential data, now let's see what is the LSTM, how it is different from RNN. And then once we understand the conceptual basis for this LSTM model architecture, then we will see practical implementation, right? So this is the idea, how we progress. Okay, guys. So let's start. So guys, LSTM model, it stands for the long short-term memory architecture. Long short-term memory. It is a type of the RNN model only, right? Which is designed to overcome the limitation of the traditional RNNs. Now, what are the limitations of the traditional RNN network? Vanishing gradient and exploding gradient, right? So vanishing gradient and exploding gradient problems. Now, with this vanishing gradient or exploding gradient, the traditional RNN networks, they won't capture the long-term dependencies. What is the meaning of long-term dependencies? So if you have a network architecture like this for traditional RNN, so let's say you have a number of hidden layers, right? And let's say here we have an output layer. So due to the vanishing gradient problem, the weights are not being adjusted for these layers. So the layers which are close to the output layer, for these layers, the weight is being adjusted. But the layers which are very far away from the output layer, like this, the weights are not being adjusted due to the vanishing gradient problem. And since the weights are not being adjusted, we are not getting the information or insights from these layers at the output. So this is what we are calling as the output cannot be captured long-term dependencies in the sequential data due to the problem of vanishing gradient. So this problem is overcome by LSTM model, right? So there is another advantage of using the LSTM model. So let's see, widely used and effective model for various tasks involving the sequential data, such as a natural language processing. That means you can analyze the text data with this LSTM model. You can do the speech recognition, time series prediction. That means forecasting. It's a forecasting. So that means you can analyze any kind of a sequential data with the help of the LSTM model. Now there is a one advantage of using the LSTM model over the traditional RNNs is that it will provide you the parallelism advantage. Now, what is this parallelism advantage? Is that LSTMs can process input sequence in parallel, which accelerates the training compared to the traditional RNNs that process the sequence sequentially, right? That means whatever traditional RNN methods or architecture we have in those RNN networks, at a time we provide only one input, right? At a time we provide only one input. But LSTM has the capability that you can provide all the input sequences in parallel. So that will accelerate the training process. So this is another advantage of using the LSTM model. Okay. So now we understand LSTM model will overcome the problems of the traditional RNN network, right? There is, okay. How in parallel? So it's like, let me just show you. So it will be like, let me do it here only. So let's suppose, guys, you want to analyze a sequential text data. So let's say, let me take the same same sentence. Let's meet on lunch. Right? Now, if you are taking the RNN architecture to analyze this sequential data, so what RNN will do, at one time instance, that means let's suppose this is your RNN network. Let's say this is your RNN network. So at time instance t, it will take input as a first word, which is let's. In the next time instance, that is t plus 1, it will take another input, which will be the meet. Next time instance, t plus 2, it will take another word as an input, which is on, and so on. So that means at a particular time instance, it will take only one word as the input. While in case of a LSTM, they have the functionality that you can provide all the words as the input at one time instance only. That means you can provide multiple inputs in a parallel. So at a time instance t only, you can provide let's meet on lunch. So this is the meaning of the parallelism, right? And this, let me just tell you, this particular property is being effectively utilized when it comes to the transformers with attention mechanism. Transformers with attention model or mechanism. So this property is being effectively utilized with this kind of a network called transformers with attention models. Right? Okay, cool. So I hope this point is clear, guys. Please explain about the parallelism in detail. So this is what I've explained you. Okay. So now if you understand why we are using the LSTM and why we prefer LSTM over RNN networks. Now let's see some internal, internal diagram or how the things are internally being adjusted in case of a RNN as well as LSTM, so that you can easily understood what is the update is being like, how the architecture differs for LSTM and RNN. Yes, Ayushman, that's the meaning of parallelism, right? Okay. So let me first show you how the internal architecture of RNN looks like. Okay. So guys, this is the internal structure of RNN. It's not an internal structure of LSTM. It is the internal structure of RNN, how RNN looks like. So to understand this structure, let me just recall you that neural network diagram. So just consider it like this. This is the input node of the first layer. Here we have a hidden layer node for the first layer, H1. Here we have a output layer node, O1. Right? This is the first input, I1. Now output of H1 will go to the output of, layer node of O1, and then this output is also goes to the work as an input for next layer hidden node, H2. And for this H2, we have a input from input node I2, and also here we have a output O2. And the output of H2 will also go to the input for next layer hidden node, H3. For H3, we have a input from I3. And here we have a output O3 node. So this is how RNN structure looks like. This is exactly same architecture what we are seeing as an internal diagram of RNN. So you can see here, guys, except the first layer hidden node, all the hidden layer nodes for rest of the layers will have two input. One is coming from the previous hidden layer output. Another is the current input node, right? So the current input from input layer node. So all the hidden layer nodes will have the two inputs. Okay. The same thing you can, visualize here also. So let's say this is a first layer, which is not visible. Let's say this is the black box. This is the third layer node, which is also black box. And each and every layer box is having this kind of a architecture only. So here we are just, seeing the internal architecture for this second layer. So if you see for this second layer node, we are getting two input. One is the first input is from the input layer. This X is nothing but the input. So input for time instance t, input for time instance t minus 1, input for time instance t plus 1. So let's focus over this particular layer, right? Let's focus on this particular layer. So in this layer, we have a two input. One input is coming from the input layer. Another input is coming from the previous hidden layer output, which is this one, right? This is the previous hidden layer output. Now these two input will get combined, right? With the help of, let's say, tanh activation function. And guys, this is a neural network. So this is a neural network which will combine these two inputs with tanh activation function. And whatever output this hidden layer node will generate, that output will go to two places. So the first places, it will go to the output of output layer node. And this output will also go to the next layer, hidden layer input, right? So this output will be the input for the next layer node. So each and every box will have this kind of an internal architecture. So this architecture is exactly same as what we draw from a neural network point of view. Understood, guys, this architecture? So except the first layer node, each and every hidden layer node will have two inputs. One input is coming from the input layer node. Another input is coming from the previous hidden layer output, right? So whatever hidden layer output is generated as a HT, that HT will go to the two places. One is the output layer node as well as the input for a next layer, hidden layer. Okay. Is this architecture is clear, guys? How RNN looks like from inside? Yes or no, guys? Let me also check with YouTube, guys. Great, great, guys. Okay, cool. So this is one thing what we have as an internal architecture of RNN. And let me share my screen again. Okay. So guys, if you understood how internally RNN looks like, let's see what are the changes have been done with respect to the LSTM. So how a LSTM model looks from inside. Okay. So this is what we have, guys, as a LSTM model. And this is the place, let me just explain you one more important point. How LSTM will overcome the vanishing gradient problem. So guys, in the case of LSTM, whatever we have as a recurring weight, all the recurring weight will be 1. So that there won't be any vanishing gradient problem and there won't be any exploding gradient problem. Right? So the recurring weight will be 1 only. So in that way, it will overcome the vanishing gradient as well as the exploding gradient problem. Now, apart from that, if you see, guys, Here we have this kind of a little bit complex architecture, but don't worry, I will explain you each and every point. Right? It will be very easy, guys, once you understand the things related to the LSTM. Okay, so just a minute, guys. Okay, why one? So actually, the researchers have tried with different values, and they analyze that when the recurring weight value is one, exactly one, so they never found the problem of vanishing gradient and exploding gradient, right? So if you multiply number of recurring weights with the value of one, let's say you have a 15 hidden layers. That means you have a 15 recurring weights. So if you multiply 15 once, 1 into 1 into 1 up to 15 times, it will be 1 only, right? It won't be very high value or it won't be very low value. So that's why we have a recurring weight equals to 1, which will overcome with the vanishing gradient problem. Yes. Okay, guys. So this is how a LSTM architecture looks like from inside. Okay. Now, just recall, guys, in RNN, each and every hidden layer node will have two input. One input was coming from the previous hidden layer output, that is from h of t minus 1. Sorry, h of t minus 1. So if it is the ht at a time instance t, so this ht will have two input for RNN. For RNN, this ht is having two input. One is coming from the h of t minus 1, the previous hidden layer node output, and the current input node. The input is from the current input node, that is from I of t. Now, in case of a LSTM, each and every node is having the three inputs, right? What are the three inputs? This is one input, this is another input, and this is another input, right? And we have a two outputs. This is the first output and this is the second output. While in case of a RNN, we have only one output from each and every hidden layer. That is the output which will be the input for next layer node, that is for h of t plus 1. While in case of a LSTM, each and every hidden layer node is having the two different outputs, right? Two different outputs. Now let's understand what is this particular architecture is. Okay. So I think as of now, you guys understood basically how LSTM is different from RNN in terms of the, vanishing gradient or exploding gradient problem, as well as in terms of the internal architecture. Okay. Now let's understand what are all these things are. Like what are these inputs and what are these sigma and tan h and these things are. So what I'm going to do, guys, I'm just taking this particular architecture for a further analysis. So I will remove this one and this one. I will only take this particular block, okay, to understand what is the LSTM. So let me just tell you a couple of important things. So let's suppose, guys, this is the layer what we have at a time instance t, right? And this was the two inputs we are getting from the previous hidden layers, right? So these were the inputs coming from t minus 1 time instance. This is the input for at time instance t, right? And whatever output it will generate, that will be at time instance t only. This is first thing. Second thing, okay, these are some interpretation. So where you see this single arrow, that is the vector transfer. That means whatever value we have at input, that value is being transferred to the next particular point. These kind of connections mean we are concatenating the input from different sources, right? Just like this. So if you just see this particular architecture, so here we have an input from h of t minus 1 and x of t. So these two inputs will get concatenated. And guys, since we are dealing with a neural network, here in the case of LSTM, this ht, h of t minus 1, all of these are in form of the some vector. So these are some vector representation, right? These are not a single value. These are some vector representation of text data, right? And then where you are seeing this, these circles either cross or plus sign, these are some point-wise operation. And where you are seeing this yellow box, so this yellow box will indicate that there is some neural network architecture. Neural network architecture means this kind of architecture. Not exactly this architecture, but it is something like you have a couple of layers as well as, connections will be there. So this is how we have this LSTM architecture. And let me just walk you through different parts of this LSTM model architecture. Okay. Now, guys, before starting with different parts, let me just tell you the name of different sections or parts this LSTM architecture has. So in the LSTM architecture, guys, we have a couple of things. We have something called as a memory cell. Memory cell. And with respect to this memory cell, we have one more thing, which we call it as a cell state. Right? This is first thing. Apart from this memory cell, guys, LSTM architecture has three kinds of gates. So if you recall, LSTM is a gated neural network architecture. So here we have three gates. Gate number 1, we are called as a forget gate. We have something called forget gate. We have another gate called as an input gate and output gate. Right? So we have these four things with respect to the neural network architecture. Now let me just show you where all of these things are, put into this architecture. So guys, this particular, whatever this line you are seeing, this vector transfer you are seeing, this is something we called as a memory cell. Right? Whatever things are present in this particular vector transfer line, that is something we are called as a memory cell. And the output of memory cell, which is the CT in this case, this is we call as a cell state. Right? So this particular, whatever calculation is going over this particular section, that is something we called as a cell state, memory cell. And the output of memory cell, which is CT in this case, is the cell state. This is first thing. Second thing, whatever operation is being performed by this particular section, this section we called as a forget gate. This is something we are called as a forget gate. Right? This middle section, this part is the input gate. This is something we called as a input gate. And this section, this complete section, we called as a output gate. Is that clear, guys? What are these terminologies? Memory cell, forget gate, input gate, and output gate. How these, these terms are arranged in this network. Up to this point, guys, any issues to understand these terms? How these terms are, fit into this architecture? Okay, cool. So I guess things are pretty much clear. Now let's see what are the, functions of these different parts. What this memory cell will do, what this forget gate will do, what this input gate will do, and output gate will perform. Great, guys. So let's see, guys. So if you understand this particular terminologies and how these terms are, fitted in this architecture, it will be very easy for you guys to understand the LSTM architecture. Okay, cool. So this is what we have. We have just taken this particular section like this. And you can see, guys, every block has three inputs. One is this ht, this h of t minus 1, c of t minus 1. So this ht is the current input. H of t minus 1 is the previous hidden layer output. And c of t minus 1 is the thing, but the cell state from previous layer, right? So ht, h of t minus 1 and c of t minus 1. And we have a two output for each and every state or each and every block. The output for the hidden state or hidden node for a current time instance t, h of t, and the current cell state, which is a c of t, right? Important thing to remember is that all of these inputs and outputs are not a single value, but vectors. So as I told you, most of the times we use this LSTM architecture for a text data analysis only. So when you are processing the text data, so ultimately we need to convert the text data into the numerical representation, like vectorization. So all of these, xt or ht minus 1, ct minus 1, these are some vector representation. These are not a single value. These are some vector representation of the input data. Okay. Now let's see, guys, the different parts of this LSTM model architecture. So we have an input layer. It will provide whatever sequential data input we have. It will just pass that input data to the LSTM model. So input layer receives sequential input data, which could be a time series data, a sequence of words, or any other sequential data, and it will just pass this input data into the LSTM architecture, right? Then, guys, we have a LSTM cell. So we call this LSTM cell as a combination of CT and HT. This particular combination is called as a LSTM cell. This is the fundamental building block when it comes to the LSTM model. Okay. So what is a memory shell? So guys, memory shell is nothing but it is the internal memory of a cell, which will allow it to store information over long sequences, right? So let me just remind you one of the disadvantage of RNN. So what was the disadvantage of RNN? It cannot capture the long-term dependencies, right? So if you have a very large network, so it cannot remember the information or the insights from the layers which are far away from the output layer. That means long-term dependencies cannot be captured by this RNN network. So this is being captured by LSTM. How it will capture these long-term dependencies? It just using the memory cell, which will store the information over a long sequences, right? So the main objective of this memory cell is to store the past informations over a long sequences. Okay. Now, second one, we have a hidden state. This is the output of the cell. It is used as an input for the next time step, just like a hidden node, whatever we have discussed. It will contain some relevant information. Now, guys, with this memory cell, which will store the information over a long sequences or past couple of time instance sequences. So as we progress with current input data, do we need to store all the past information? No, right? Sometimes what happens, we need to delete some information which is not useful, right? And we need to add some new or current information which is relevant for upcoming data, right? So that means whatever information this memory cell stores, this information is being updated time to time. So some information will get removed from this memory cell, which is not relevant, and some new information which will be relevant in upcoming time instances that will be stored. So this functionality is being performed by forget gate. So we have a three gates, right? Input gate, forget gate, and output gate. So input gate will control the information that is stored in the memory cell. That means what information will be will be as an input to this memory cell that is being controlled by input gate. Forget gate will control or will decide what information should be discarded, right? So it will decide which information it should, discard or remove, and which information it should keep from the past sequences. So this is with respect to the previous time instances. So whatever information or data we have from the past time sequences, which data we should keep forward and which data we should discard or remove. This is something decided by the forget gate. Input gate will decide what new information will be get as an input in the memory cell, right? And output gate, which will determine what next hidden state should be based upon the cell state and the input gate. So this is the output for the next layer node, right? So output gate will contain, there are two outputs. One is the cell state output and hidden state output. So that will be the input for the next block. So this is the functionality of these gates. And that's why we are called as the LSTM as a gated neural network architecture. Is this explanation is clear, guys? The functionality of each and every block in the LSTM. Any questions, guys, with this part? Okay. Okay, once again, explain the forget gate. Okay, let me just explain forget gate in a detailed manner. Okay, guys. So let me use this one. So, okay. So what I'm going to explain, guys, how the forget gate will, it will discard the previous input or it will keep the previous information. Please remember, forget gate will only discard or keep the past information from the past time instances. Input gate will, it will provide input from the current instances. Okay. So here I'm going to draw a partial, block of this LSTM architecture. So I will only draw the forget gate. So let's say this is the LSTM block. And this is how we have a forget gate. This is the input cell state from C of t minus 1. This is the hidden state output from the previous time instance, h of t minus 1. And then here we have a pointwise operator. And we have an input from this neural network with sigmoid as an activation function. So the guys, this sigma is nothing but it is a sigmoid activation function. And there is a input to this neural network, and which is the input from this time instance t, which is a xt. And this is something we are calling as a, okay, so there is one more thing, and this is, it will go further. So this is something we call as a forget gate. Right? Now, as I told you, whatever inputs we have, this cell state, this hidden layer output, and this current input, all of these are some vector representation. So it's like 1, 1, 1, 0, 0, something like that, some values, some vector representation we have of all these words, right? Since it is a neural network. So like at the backend, guys, here they are using sigmoid as an activation function. Now this sigmoid is an activation function which is used for a classification purpose. So that means it will classify the records either 0 or 1. So it will use a vector, something like either 0 or 1 form. So let's suppose we have a vector like 1, 1, 1, 0, 0, 1, 0, 1, something like that. We have a vector like this. So this is a, let's say, a vector representation of this sigmoid activation function over this neural network. And let's say whatever information we are getting from, this cell state, let's say this is some previous information. So we have a 1, 2, 3, 4, 5, 6, 7, 8. So let's say we are getting some previous, past information in vector form. So let's say this is 11, this is, let's say 13, this is 9. Let's say this is a 5, this is a, let's say 12, this is 8, let's say this is a 31, 1, 2, 3, 4, 5, 6, 7, and let's say this is a 10. So this is some numerical vector representation of the past information what we are carrying in this C of t minus 1. Now here we have a pointwise operation. So pointwise operation is nothing but it will multiply these two vectors position by position. So it's a position by position multiplication. That means the first value will get multiplied with the first value, second value will get multiplied with the second value, and so on. So what is the output it will generate? Now, before getting the output, let me just remind you once again. This is the vector what we are getting because of the sigmoid activation function. This is the information which we are carrying from the past time instances, which is the information stored in the memory cell, right? Over a longer time sequences. Now, here we are going to discuss how this forget get will keep certain information and how it will discard certain information. So depending upon the weights present in this particular neural network, so this is a neural network. This sigma activation function is the neural network architecture, right? Now, what it will do, it will do pointwise multiplication. So the 11 will get multiplied with the 1. The answer will be 11. 13 into 1, 13. 9 into 1, 9. Now we have a 2 zeros here. That means next two information will get discarded. So 5 into 0, 0, 12 into 0, 0. And then 8 into 1 is 8. 31 into 0, it will be 0. 10 into 1, 10. Now see, whatever operation this neural network will perform with this C of t minus 1 previous memory cell output, now it will update this C of this cell state as a CT, which will this particular value. So this is the new vector based upon this particular neural network at C of t, right? So now you can see, guys, here we have discarded information like these two, 5 and 12. This is the vector representation of the information text data, right? 5 and 12, and this 31. So this information is being discarded based upon your neural network architecture. So in that way, this forget gate will work. So it will discard the information which is not relevant for the network, and the rest of the information it will keep and it will progress. And then here we have an input gate, right? So the input gate, here we have a pointwise operation as a plus, adding operation. So this input gate will add certain information to this cell state so that it will get updated, and that is the final output of the cell state. So in that way, this forget gate and input gate will work. Is that clear, guys? Any issue to understand this internal functionality, how these gates will work? Welcome, guys. Welcome. Yes. So this is how this forget gate, input gate will work. Okay. Let me also check with YouTube, guys. Okay, guys, don't worry. Whatever PPTs or like notebook, Jupyter notebook we are discussing, all of those things will get shared to you guys. Don't worry about it. Okay. But whatever architecture I am drawing from my side or explaining from my side by writing it over the screen, that is something, if you if you think this is important, you can note it down. Otherwise the recording will be available to you guys, so don't worry about the materials. Yes, Nikhil. So working of the gates, let me just recall you. Just a minute, let me see a couple of other questions. Okay, let me share my screen. So let me just recall you all of these things, guys, in short, right? So this is something we have as a forget gate. This is something we have as a input gate. And this is something what we have as a output gate. And this particular part we call as a memory cell. And the output of memory cell is a cell state, right? So what this forget gate will do? This forget gate will take input from h of t minus 1 and x of t minus 1. It will just combine these two outputs. And guys, it's a vector operation, right? So whatever output it will get, it will pass this output to this neural network with sigmoid as an activation function. Since it is a sigmoid as an activation function, so it will generate the output like either 0 or 1 form, just like this. And this output is being point-wise multiplied from the previous memory cell output. That means previous cell state. So from the past nodes, whatever information is stored, that information is getting multiplied with this current neural network output with the sigmoid as an activation function. So when this information is being multiplied, where you have a zeros, all those information will get discarded or deleted. And where we have these ones, so only this information will get processed for the next processing, right? So whatever output we are getting here, over this output, the input gate will add certain recent informations. So it will be a point-wise addition, right? So whatever input gate will provide the output, that output will get point-wise added to this current cell state, and whatever output you will get, that is the updated cell state at time instance t. Okay. By example, Nikhil, it will be very difficult, to do all the calculations, since the calculations are not easy. So it's a vector operation. It will be very much complex, right? So there we have a number of, like vector operations, like transpose of the vector and do some vector space, what you call multiplication and so on. So there will be a lot of operations are there. So it's not very easy, like to explain by taking an example. But yeah, this is the overview how it will perform each and every part of this LSTM architecture. Okay. So with this, guys, so okay, and any questions, guys, with this part? Anyone? Don't worry, guys. You will get the attendance link in the chat box by 8:30. Don't worry. Okay, guys. So let me just walk you through one of the uh, you know uh, hands-on practical case for this LSTM neural network. For that, just give me 1 minute so that I will be ready with the materials. Just give me 1 minute, guys. Okay, guys. So let me share my screen. I hope my screen is visible to you guys, right? Yes or no, guys? Cool. Okay. So, guys, we will cover two examples. We are going to cover two examples with this LSTM neural network architecture. One with the numerical data, right? That is a sequential data in a numerical form, and another one will be the sequential text data. So in today's session, I'm going to cover how we process the sequential data, which is the numerical data with this LSTM neural network architecture, right? So guys, here, this particular case study is related to the stock price prediction using the LSTM model. Okay. So we are going to predict the stock price, and I'm sure all of you guys know this stock price is being updated with respect to the time, right? Each and every day. So at the day end, it is being updated. Please explain ilog function. I'm confused. Okay, Ashman. After the session, I will like explain this ilog function. Okay, don't worry about it. So for the time, let's focus over this particular case study. Okay. Okay, so okay, you are asking about this ilog function, okay, right here. So guys, ilog is so we have two functions actually, log and ilog. So these are the two functions through which you can filter out your data. That means you can select the number of variables you want to fetch from your data, or you can also select the number of rows. Okay, so these two functions are used to filter out the records from your input data set. This is first thing. Second thing, basically, ilog we use. So if you want to fetch the records, either it may be the rows or it may be based upon columns. So if you want to fetch the data with respect to the index position, so for that we use the ilog. If you want to fetch the records based upon the column names, right? So there we use log operator. So you see here we are using the ilog, and here we are providing the index position. So this is the main difference between log and ilog. Anyways, so guys, this is what we have a Google stock price train data. I have two data set. One is the Google stock price train data, and another one is the test data. So I already have a train and test data with me. So here I'm not going to perform train and test split. Okay. But if you don't have a train and test data separately, you need to perform the train and test data split, what we have discussed in yesterday's session. Okay. So since in this case, I have a train data set as well as the test data set separately. So I can directly build model over the train data set, and I can test that model over the test data set. So guys, this is the data what we have. In total, I have a 1258 records with 6 features. So this is a Google stock price data set where we have a all this data is being indexed by the date column, which is a one kind of a time base. So date we have a for each and every day we have a Google stock price open value, high, low, close, and total number of some volumes. Okay. Now in this particular data set, my target variable is this open variable. So we need to forecast what will be the, for next day, what will be the open price. Okay, so this is what we are going to perform with this data set, and this data set is indexed by the time. So that's why it's a sequential data set. You can't change the order. Okay. So what we are going to do, we are just fetching my target variable, which is this open variable, right? So this is we are calling as a this training data set, training set as a target variable. And over this variable, we are going to apply the LSTM model. But guys, if you recall from the yesterday's session, if you want to build any kind of a deep learning or AI based model, there is something called feature scaling, which is compulsory, right? Feature scaling is nothing but it is also called as the standardization or normalization. So under sklearn dot pre-processing module, we have a something called as a min-max scaler. Okay. So with this particular min-max scaler, we are just scaling our target variable, and this is what we are got as a scaled value. And this feature scaling is compulsory if we are building any kind of a deep learning architecture. Okay. Now let's see, guys. Here comes the interesting part. The data processing before building the model, the data processing or data preparation for LSTM model is quite different from rest of the data set. How? Let's understand. So, for example, let me show you from here. For example, guys, let's suppose this is my, okay, let me just show you. Okay. Let's say, guys, this is my data set over which I am going to build the LSTM model. Okay. And let's say I have applied all the, required, like whatever conditions we have, like feature scaling or whatever we have applied all those things. So before building the LSTM model, here comes one additional concept, the concept of data preparation. So in case of a LSTM, how the data is being prepared, let's understand. For that, guys, first of all, you need to select something called as a window size. Window size. Now this window size is nothing but it will tell you how many past time instances you want to consider in LSTM model so that it can remember the previous information up to that time instance. So let's suppose if I apply window size is equals to 10, that means it will recall, or in the memory cell, it will remember past 10 time instances information. This is something we are called as a window size. And based upon this window size, it will prepare the input data for LSTM model. This window size is also called as a time stamp. Time stamp. That means previous how many time stamps data you want to consider for LSTM to get, it will recall those information. And let's say I'm selecting time stamp is equals to 10. Let me just make it 5 so that you can better understand. Okay. So guys, if my timestamp is 5, so how the data is being prepared, let's understand. Please guys, please focus over this particular point. It is important. So what I'm considering, these are all my, input values for my target variable. And let's say after 322, we have a 790 for time instance. So what it will do, guys, it will pick first 5 records. And what are the first 5 records? Let me like this. It will pick first 5 records because my window size is 5. So 1, 2, 3, 4, 5. And it will make it like it will transpose this column format into a row kind of a format. So it will be like 325, the first value, second value 331, 329. Then we have a 328. And then we have a 322. Now, all of these 5 values will be the new input for my data set. And against this input value, the output will be the next value. Let's say the next value is 790. that is the output value. So LSTM will consider this as the output value and all of this as the input value if my time instance is 5. And what will be the next record? So the next record will be the next 5 values. So let's see what will the next 5 values. Next 5 values will be 333, 330, sorry, there's a high, which one? 331, 329, 328, 322, and 790. These are the next 5 values. That means 331, 329, 328, 322, 790. These are the next input, and against this next input, the output will be the next value, which is the again 790. This is the second row. The third row for the input data will be next set of 5 values. So what is the next set of 5 values? It will be 329, starting from 329 to this, right? So it will be 329, 328, 322, 790. Again, we have a 790. And the output corresponds to this input data will be next data point, that is a 793. And in that way, it will generate this kind of a data set, which is the input for LSTM architecture. So this is the additional thing we have, data preparation in case of a LSTM model. Now, it totally depends upon what window size you guys select. Based upon that, it will generate this kind of a data, which is the input for the LSTM model. Right? Is this process is clear, guys? How the input data is being prepared? Yes or no? What do you mean by the okay? So, Sumona, as such, there is no limit for this max or minimum window size. It totally depends upon actually what we do, we take different window size because we don't know what is the optimal value of this window size, right? So what we do, we take different window size for the neural network architecture, and we run this model and we analyze the result. So whichever is providing me the most optimum result with respect to the business case, that window size we select for a final model. Okay. Is that clear, guys? Okay, cool. So this is with the case of the numerical data. Okay. The same thing, guys, it will do with respect to the text data. So if it is a text data, so let me just show you an example. Okay, let's take this particular sentence. Stock price prediction with deep learning using LSTM. And let's say we specified that my time instance or window size is 3. So just like whatever operation or concept we saw how it prepares data with numerical data, same thing it will apply over the text data. So for text data, if the window size is 3, it will prepare a data like stock, then price and prediction. That means window size is 3, right? So the first 3 words, stock, then price, and then prediction. If this is the input, then output will be your next word, which is a with. And this is the first row. And the second, for the second row, the input will be price prediction with. Price prediction with. And the output will be this D. So this is how it will prepare the data for the with respect to the sequential text data. And guys, let me just recall you, this is not it is not a word, rather than these words will get converted into its vectorized form. So it will be some vector representation of a stock, vector representation of this price, prediction, and with. Right? So it's not a text information, it's a vector representation of all these words. Guys, attendance link is there in the chat box. You can fill the form and mark your attendance, right? So I hope this process is clear. With the window size 1, any stock can be made. Yes, if the window size is 1, so it will just same data, right? Okay, so let's pause, guys. In this particular example, I am taking the 60 time steps, or window size is 60 with only one output. Okay, so this is what we have a logic how you prepare the data. So if your window size is 60, you need to apply the logic so that it will be prepare the data just like what we have discussed. So this is how it will discuss, and it will prepare two things. One is your X data set, another one is your target variable Y, right? So this is what we are getting: X train and X train and Y train. And rest of the things are exactly same what we have discussed in yesterday's session. So, one more thing, guys. Here, in case of LSTM or RNN, just a minute. Oh, yeah. In case of a LSTM or RNN, there is one more important thing. You need to provide the input data in a specific format. So it's not a data frame which is having the rows and columns. Rather than here, the shape is different, which is in form of the 3 parameters. First one is a batch size. Batch size is nothing but the number of records. Second one is a timestamps, right? And the third one is the indicators. So indicators are nothing but the how many outputs you want in the final forecasted values. So this is the format. This is my format. So batch size is nothing but a total number of records. Timestamps is nothing but the 60. And then we have only one output. So you need to reshape your input data before applying to the LSTM or RNN architecture. So these are the couple of changes present in this particular LSTM model building. Yes. So here we don't provide the data set in rows and column form. So you need to reshape your data into this, 3 indicators. Okay, then each and everything is very simple. So you need to import whatever model you want to build. So we are importing sequential model, dense layer, LSTM model, dropout and all, if you want to apply these layers. And the things are very much simple. So just start with the, import the, just take an instance of this sequential model, since neural network is a sequential neural network. And then start adding the layer. Since here we are, adding the LSTM layer. So under the add function, you need to specify LSTM so that it will be a LSTM layer, right? And if you recall, ultimately, it is a form of the RNN, okay? So you have a recurrent connection available. That means you have a feedback, this particular feedback to the hidden layer. That means output of one hidden layer will be the input to the next hidden layer out, right? So that is being adjusted with something called the return sequence equals to true. So by making the return sequence equals to true, it will adjust the output of one hidden layer will be the input to the next hidden layer, right? Just by specifying return sequence equals to true. And you need to specify here we are using the LSTM layer. Okay. You can also use the dropout layer. So this is how we are using the dropout layer. So what this layer will do? It will drop 20% connections between this layer and the next layer. So it will drop 20% connections between these two layers. Okay. And here I'm, specifying a couple of hidden layers and output layer. And then you need to compile this RNN architecture or LSTM architecture. That means you need to specify optimizer as well as the loss function, and then execute this. Right. And once you have executed, you can use this model to get the prediction over the text data. So, but before applying over the text data, you need to perform the same data pre-processing steps what we have applied with the train data. That means just prepare the input data set and provide the shape of the text data same as the input data shape, and then do the prediction. And this is what you are getting as a predicted stock prices, right? So this is what we have, guys, as a LSTM neural network exercise. Okay. So two more important things is here with respect to LSTM. Let me just remind you. One is the data preparation with respect to the LSTM based upon time instances, and then uh, shape of input data. So this is something you need to take into the consideration when it comes to the LSTM neural network. Okay. Cool, guys. So with this, any doubt, guys, or any queries? Anyone? Great. So this is what I have for today's session, guys. I'm sure you guys understood how LSTM architecture, you know, uh, it is different from RNN architecture internally, and how the different forms are how the things are arranged in terms of the LSTM architecture, like memory cell, forget gate, input gate, and so on. What do you mean by final topic, Sumona? I didn't get your question. Partial and exploding. What is this partial? Yeah, we have discussed epoch, right? In yesterday's session, we have discussed what is this epoch. So we have exactly same thing here. Okay, cool. So if you guys have any questions related to the LMS or study material, so over to Amar.
Yeah, sure. Thank you. So participant, I have an announcement. If your friend are looking for a Python and SQL course from the Excel solution, so we're starting our next program on Python and SQL for 30 hours from 27th of the November. So I'm sharing that link with you so you can share with your friends. Prabhakar, timings are 7 p.m. to 9 p.m. Attendance, yeah, sharing the attendance. Okay, sir. My one known person at the Chennai, I can tell them also. Yes, you can share with your friends, family members, and your college, those who are looking for to upgrade their skills in the Python programming skill. Himanshu saying our college kids inform us about your quality courses. Thank you. Prabhakar, it's free of cost for 30 hours. Guys, I shared the attendance link once again. Dates 27. Pratiksha, we're going to start that program from 27th of the November. Himanshu, I hope what you heard, what your college is told to you, that's all things are here. When this course will be finished by next weekend. guys, anything else? Material, you can check our LMS, it's already there. Okay, so thank you so much, my dear participant, for attending the session, and we'll meet you on tomorrow